Hello, everyone. This is Jeff Clune. It's a pleasure to be here. Thank you to the organizers. I want to tell you today about how we might produce very capable AI and a new paradigm that I have on that front called AI generating algorithms. I think AIGAs are a very unique opportunity, in particular for this community of people hybridizing evolution and reinforcement learning. And so I want to tell you about a broad swath of work that we and others have done in this space, as well as a deep dive into Go, Explore, and Poet toward the end, which are interesting examples of this kind of work. So AGI, or human level AI, has been one of the grandest ambitions of our field since its inception. I think we have a long way to go, but I still think it's instructive to think how we might get all the way there. And I think if you look to the traditional machine learning community, what you see is what I call the manual path to AI is dominant. And this involves basically identifying individual building blocks of AI that we think we might eventually need. So if you look to most of the main ML conferences, what you see are papers that say either, here's an improved version of one of these or another building block, or here's a new building block that I think we should add to the set. And just seeing this list, it's daunting to think about, how many more are out there? Are there hundreds? Are there thousands? Can we identify them all one by one? And even if we could, then there's this other project we have to do, which is we have to put them all together and think about combining all of these hundreds or thousands of parts into some giant, complex Rube Goldbergian thinking machine. That is a Herculean task. And I think we should be clear-eyed about how hard it is. Not necessarily impossible, but very hard. Debugging that would be a nightmare. Optimizing that would be a nightmare. And it probably would require an entire team on the order of a CERN or an Apollo project. However, if you look to machine learning, there's a very clear trend, and that is that hand-designed pipelines give way and are replaced by entirely learned pipelines once you have sufficient compute and data. We've seen that with features in deep learning, such as vision or natural language processing or speech recognition, where you go from things like hog and sift features to learning them end to end. Increasingly, we're seeing architectures learned, hyperparameters and data augmentation pipelines learned, even the RL algorithms being learned themselves. And all of this suggests an alternative path, which is that we should go all in and learn as much of the solution as we can. And that I call an AI generating algorithm. The idea is learn as much as possible, have an algorithm that starts with simple origins. It's not very smart at the beginning, and it has to bootstrap itself up to produce increasingly sophisticated and intelligent agents until ultimately it produces something that's very, very intelligent. That could be done through an expensive outer loop that's searching through the space of agents, for example, and ultimately produces one thing or a set of things, which is a very sample efficient learner. Now we know that this can work because it happened on Earth with a very simple, unintelligent algorithm of Darwinian evolution, searched through with a planet-sized computer, a huge search space, and ultimately produced the human brain, which is the most impressive learning agent that we know of. So if we want to make progress on this, I think we need to simultaneously push on three pillars. The first is to meta-learn the architectures. The second is to meta-learn the learning algorithms themselves. And the third is to automatically generate effective learning environments. So I'm going to describe each pillar, some work in that pillar, and the opportunity for this community. First, to pillar one, meta-learning the architectures. So we all know that architectures matter a lot, and we've probably all thought to ourselves that we should search for them. In fact, this work has been going on for a very long time in our community. For example, most famously by Ken and Risto with the NEAT algorithm. Historically, that was done in our community in very tiny neural networks, like on the order of dozens or hundreds of parameters. Now compare that to GPT-3, which has 200 billion parameters. So the scale has gotten bigger, but the idea is the same. And so the focus now is on deep neural nets, which is increasingly called neural architecture search. But much of this work is still evolutionary work, including most famously by Esteban Real, who has this awesome paper where they search for deep neural net image classifiers, and they ended up beating the then state-of-the-art and ImageNet, which was the most popular benchmark, with an evolutionary algorithm searching for architectures, which is very promising. Risto has also done a lot of work with his collaborators. There's also exciting differentiable neural architecture search work out there that could take a lot of our ideas, but do them with a different flavor of optimization. And so I think the lessons from all of this work is that it increases my confidence in AIGAs, as I mentioned, because you can basically do things that humans are currently doing them and replace them with a search algorithm, a learning algorithm. And from a research strategy perspective, it offers a bunch of different options for people in our community in terms of how we should best harness the unique resources we have. One is you could take classic ideas from our field, such as just searching for architectures, and scale them up. Another one is you could take our ideas, such as complexification, and you could figure out a differentiable way to do that. For example, Thomas McConey has a way to do differentiable complexification in neural architecture search, which I encourage you to look at. You could hybridize, ideas from the two communities in some other weird way, or you could just use neuroevolution and evolutionary computation as a sandbox to quickly de-risk and prototype and play with ideas, because it's so simple and easy to do. And then later you could take them to scale. And any of these options are available to you, and you'll see a lot of work that kind of is in these different camps in the rest of this talk. One example is generative teaching networks, which is done by this set, which is kind of a weird and fun idea. It was gradient based, but it shows the idea of kind of starting small. And we had another paper with a scrambled shuffling of these authors called Synthetic Petri Dish, which is very cool, based on a cool idea Ken had. That also, I think, is something that people here might be interested in. I just wanted to flag it. But I want to push beyond the neural architecture search, because I think people understand mostly what's at stake there and how that works, to the other two pillars. And the second pillar is more exotic. This is the idea that we should learn the entire learning algorithm, which I find tremendously exciting. And the idea is, this is a very hard problem, so let's just let machine learning do the heavy lifting for us. So there's two major camps, at least, that are popular in meta learning right now. One of them is that you meta learn a good set of initial weights, and then you use SGD later to just do normal SGD learning. And that initial set of weights actually surprisingly has a major impact on what will happen later. And the other one is that you do all of the learning within a giant recurrent neural network. And I want to tell you about that one because I find it so exciting. So the idea here is that you have an outer loop. It could be evolution, could be something else, gradient based, and you're just going to optimize the parameters of a recurrent neural net, for example, and you optimize it for some measure of lifetime performance. And that's it. You basically, on the outer loop, you're going to change the weights. On the inner loop, you just run the thing and you see how it does, and you score it according to how well it did, and then you use that to make choices in the outer loop for how to update the weights. The cool thing there is that because a recurrent neural network is Turing complete, it technically can implement any learning algorithm. And now, theoretically, that's true of many systems that don't end up doing much impressive things, but this one actually is different. There has been studies that have shown that at small scale currently, in terms of its capabilities, it is doing some very impressive things. So it can learn to explore on its own. It can learn to exploit on its own. In the Rubik's Cube paper, which uses to great effect, it conducts experiments to figure out what world it's in, and then it uses that knowledge, which is stored in the activations of its LSTM, to then do something different. So that's learning in a nutshell, and it figured out how to do that. And something that I find is particularly exciting is Jane Wang showed that it can actually build a model of its world and do some rudimentary planning in that model, and then take action. And so it's built model-based learning, and it's also probably got model-free learning, and it's figuring out how to interoperate between the two of those, all kind of just happening on its own. Machine learning is figuring out how to do that, which I find very exciting. If you've read Thinking Fast and Slow, you'll know that that's basically what humans are doing, but figuring out exactly how to do that is hard. So let's let machine learning do the heavy lifting there. So historically, lots of the work in this area has actually been done in our community. So we've been involving recurrent neural networks for a very long time. Sometimes we explicitly are focused on learning, and you have like work by Andrea Soltoggio, Sebastian Risi, Ken Stanley, et cetera, explicitly focused on that. But pretty much any work that has a recurrent neural net in it is doing this by default. And so that's super exciting. So I think this is a huge opportunity for our community to basically, leave the small neural net area and just scale it up and see if we can apply a lot of our ideas at scale. Now, how do you do that and still use evolution? Well, if you're really interested in evolution, then you can use evolution strategies, which Salomons et al. Shows works quite well for very deep neural networks. You can use the deep GA work that we did out of EvoRL Labs, which also was competitive with state-of-the-art Atari RL algorithms at the time. Now, why might you want to use evolution? Well, first of all, I don't think you should limit yourself to that. But if you but there are reasons to, which I think are interesting. And one of them is that it really optimizes for what you care about, which is lifetime performance. Like how much reward do you get through your whole lifetime? It doesn't have to distort reward with a discount factor that really can kind of create pathologies of only caring about things in the short-term horizon. If you have a really, really long lifetime, you don't only care about the beginning, you care about the whole thing, and evolution will directly optimize for that. It can also do some other things like continual learning, which I'll talk about in a second. Another thing is evolution is very simple. You just prototype it up, try it out. You don't have to think about making everything differentiable and like the stability of gradients, et cetera. There are other cons, of course, but it has those benefits. And finally, you also have more degrees of freedom. You don't have to make everything in your system setup differentiable. So if you wanted, for example, to combine pillar 1 and pillar 2, you could use evolutionary search as well as the RNN, do complexification, all of that, just go. You don't have to figure out a differentiable way to get that all working. So that's quite nice. So if you think about all the things that learning a learning algorithm could do for you, everything that's colored here in blue is something that could be learned inside of a recurrent neural network. And then we wouldn't have to put that all together, which is quite exciting. So, we had a paper recently that I want to highlight. It was a gradient-based paper, but it still kind of has this philosophy, which is we should directly optimize for the things that we want and let machine learning solve the problem. And I think it could be combined with an evolutionary algorithm, which is one of the reasons I want to mention it. So this is paper Learning to Continually Learn. So in machine learning, one of the Achilles heels is that if you learn things sequentially, as animals, including humans, do, then you first learn task A, then you learn task B, et cetera, and you may want to come back to task A. Well, the problem is that all current machine learning algorithms, by default, when they learn B, the second task, they will do so with all of their parameters, and therefore they will overwrite everything they knew about how to perform task A, which is why machine learning systems forget catastrophically. And so we must solve catastrophic forgetting to let robots be in our homes and just kind of learn in a sequential manner and learn from us, to learn one task, go back to another task, and then go back to the first task and pick up where they left off, et cetera. So over the years, many people have worked on this problem, and all of the solutions, I would say, are manual solutions. Here's a bunch of options here. And in particular, you might think about sparse representations, where somebody's like, I think sparsity should help, but I don't know exactly how to get the optimal type of sparsity vis-a-vis continual learning. So I'll put in an auxiliary function that says reward sparsity and solve the problem. Well, the problem with that is that doesn't give you exactly what you want, because the system doesn't know what you ultimately want. It just tries to give you sparsity, even if it's counterproductive to your ultimate aim. So our hypothesis, which is in line with the bitter lesson of Rich Sutton, is that humans, we can't figure this all out. Let's just let machine learning figure it out. It's just so complicated. And so let's just optimize directly for what we want, which is lifetime learning. So we're going to learn a sequence of tasks here, and then at the end, we're going to measure performance on all of the tasks, not just the last task seen. And so, in terms of the two camps of meta learning, we ended up doing this with the first camp, but I actually think it'd be really, really profitable to do it with the second camp and potentially with an evolutionary algorithm. And so here, we were inspired by this work that came out of this community, the neuromodulation work of Andreas Otoju that was done with evolutionary neural nets at small scale. The idea here is that one neuron or a set of neurons could gate the learning of other neurons within the network, turn the learning on or off. And my collaborators at the University of Wyoming and I basically show that with evolutionary algorithms and small neural nets, you could use this to perfectly solve catastrophic forgetting. A cartoon example is that when you're playing chess, you turn learning on only in the chess part of the network and not everywhere else. And so you don't cannibalize the knowledge somewhere else. And then when you switch to a different task, you do the same. However, this was all done with really small neural nets. So in the work that I'm currently talking about, Learning to Continually Learn, we introduced this new algorithm called ANML, which uses neuromodulation, but combines it with gradient-based methods and deep neural nets, and basically just scales it up. And ANML basically performs really, really well. So if you learn a sequence of class, here up to 600 classes in a row, and at the end of any number of them, say 200 or 600, you'll measure performance on average across all of them. What you can see is that deep learning is terrible. After 50 tasks here, basically, by the end, on average, it performs basically 0 on all of them. It probably performs really well on the very last task and terrible on all the rest, which is why its average performance is so low. ANML is here in blue, and what you can see is, in contrast, it learns remarkably well. All the way up to 600 sequential tasks. Here, is recognizing different omniglot digits. or classes of digits, you know, it basically can learn 600 things in a row and still perform well on average across all of them, which is a huge, huge, huge step up from traditional deep learning. So what's also really cool is it learns sparsity. So any individual image only lights up a few of its neurons here, which you can see in the left 3 columns, but on average, it's using all the capacity within its neural net bank. Whereas when you go with that manual path solution of directly having an auxiliary loss for sparsity, it's like having an overeager student. It's like, oh, you want sparsity? Fine. And it ends up like not even using a huge chunk of its neurons because it thinks you want things to be sparse. It didn't know what you really want is to kind of solve continual learning, and that may involve sparsity. And so the sparsity thing doesn't perform as well, and it ends up producing a lot of dead neurons. So I think that the implications of this are really cool. First of all, it works really well to optimize directly for what you want, and evolution plus RL is one way to do that. I also think that it's cool that it basically, you know, it's not like it invented something totally different. It did invent sparsity, but it kind of did it in a better way. And so probably a lot of our ideas are clever, but it's just going to figure out a better version of those ideas and how to weave them together. It's probably learning how to do sparsity and many other things. I think so. Therefore, I think it validates the AIGA paradigm, which is we should let machine learning solve our biggest challenges. And so another interesting thing I think about this work is that the ideas were de-risked in evolution and neuroevolution at small scale first, and then they were scaled up. And so that is one potential path for this community. I think as I already mentioned, a really nice opportunity here is to go to the other camp of machine learning and say, hey, I really want this to happen, but I want it to happen within a giant recurrent neural network, and maybe one that's complexifying over time, et cetera. So let's use evolution to try to go after that. The thing I want to draw your attention to now, switching gears a little bit, is that even if you do take on this AIGA path, that you still have to make choices, right? You still have to give it the building blocks and the search space. And so one of the things you have to decide is what are the materials of the neural net going to be made out of? Most meta learning and deep learning uses normal neurons with SGD, for example, in a recurrent neural network. But Thomas Bocconi has done some really interesting work where he's figured out basically how to do a gradient-based version of Hebbian learning. And once that is done, you can take a lot of the ideas that we've had in this community where we were evolving Hebbian networks, and now you can scale them up to really, really, really massive deep neural nets. And so I encourage you to check out that work. And not only did he do that with normal Hebbian neurons, but he also figured out how to do it with neuromodulated Hebbian learning. So again, where neurons can change the learning that happens somewhere else in the network, but now it's Hebbian learning that's being modified. So this is a totally different paradigm from SGD, and yet it's all being done with backprop and SGD, ironically, kind of in the outer loop, but in the inner loop, it's all Hebbian learning. And so there's just a different profile of things that these networks are good at. And maybe somebody here could scale them up and do really wonderful things with them. So I encourage you to check that out. Perhaps the most ambitious version of this pillar 2 idea of let's just learn the whole algorithm was done with evolution by Google Brain and Esteban Real again, where he basically evolves the entire learning algorithm. So a bunch of really simple primitives, basically like math operations, and they invent machine learning algorithms. This is an extremely broad search space, and it reinvents, they show a cross training. It basically like slowly figures out major innovations that we have as a community invented by hand, and it does them all automatically. So it invents the multi-layer perceptron, it invents backpropagation, then dropout, then gradient normalization, and weight averaging. It also customizes these techniques to different problems. So maybe if a problem benefits from dropout, it invents it. And if it doesn't, it doesn't. So this is really extremely powerful in terms of using evolution to automate basically AI generating algorithms, or at least one of the pillars of them. So basically the same set of authors plus a few others also applied the same technique to reinforcement learning, and they evolved RL algorithms, and it also reinvents many standard RL techniques and recent RL techniques, which is tremendously exciting. I now want to switch gears to talk about pillar 3. I actually think this is the most exciting pillar for in general, and also for this community. It's the least explored and therefore has the most low-hanging fruit. I also think it best takes advantage of our community's unique background and expertise. It is a tremendous opportunity to showcase the benefits of quality diversity algorithms and open-ended algorithms. And I'm going to show you some examples of that. So, you know, for those of you who have not kind of drank the Kool-Aid yet on quality diversity algorithms and open-endedness, I'm going to take you through a little bit of the backstory, and then we'll get into some of the newer work. So, there's a paradox in life and in machine learning, which is that if you try too hard to solve a problem, you'll fail. If you ignore that objective completely, you're much more likely to succeed. So take technology, for example. If you go to this old cooking pot over a fire and you say, I will only fund research that can heat up food with less smoke and faster, then you will never invent the microwave, because to invent the microwave, you had to have been working on radar technology and notice that it melted a chocolate bar in your pocket. And radar technology was not being studied because it makes you cook faster. Similarly, with an abacus, if you said, I want that device, but I now want to fund only research that will increase compute per minute, then you might get longer rods and more beads, but you will never invent the modern day computer, because to do that, you had to have been focusing on vacuum tubes and electricity, which again, were not invented because they make computing better. So you have to give up your goal to get your goal, which is pretty cool. The same thing applies with to get clean energy. You have to be thinking about the speed of light and trains and clocks and things. So the conjecture here is the only way to solve really hard problems, maybe by creating the problems while you solve them in an expanding set and goal switching between them. If you're working on one problem and all of a sudden you get a good solution to another problem, go with it. Don't just get stuck. Don't throw that out and say, I know I need to stay stuck on this particular problem. And that is this idea of goal switching. So if you're trying to solve one task and you suddenly start making progress on a different task, like let that happen also. Add that to the set of things you're willing to work on. For example, if you're a roboticist and you're trying to encourage a robot to walk and you are optimizing for that, and you suddenly get a robot that's really good at crawling or balancing, don't throw that out because it's not walking behavior. Keep it, because it may be a stepping stone that ultimately gets you to walking behavior. And so quality diversity algorithms are really built on this idea. We wanted to produce a diverse set of high performing agents that are each really good at different things. And so one of the algorithms that is being used a lot in this space is MapElite. I'm going to talk a little bit about it. The general idea is that you take a search space, you discretize, certain dimensions that you're interested in, you discretize those, and then you find the highest performing thing everywhere in that space. So if you, take classic optimization and you see how it searches. Here's the soft robot problem where you had these like Jello robots running across the screen. Classic optimization produced low performing solutions, and it didn't explore the space much. Including, here we're measuring 2 arbitrary dimensions that it didn't know to care about, but we looked at, and it didn't explore like the percent of bone and the number of voxels. If you do, if you add a diversity pressure, including specifically with respect to these 2 dimensions, you get higher performing solutions, which we've known for decades, but you still don't really explore the search space very much. MapElite is like a total qualitative difference in this department. It really fans out, explores the search space. When you ask it to explore these dimensions, it says, okay, I will do that. And it teaches you so much about the search space, like where all the different local optima are. It also ends up producing often better solutions because it harnesses goal switching and produces these circuitous routes through the search space. In fact, if you look at any point in this search space and you say where, what path was traced to get there, it is not the case that optimization just produced the best solution by only working on that goal. And this is like doing that in parallel. Goal switching is essential here. You see, to find the best final solution at any point took this long circuitous path through the search space to figure out how to get there, which I think is very interesting. So this idea was used to great effect in this paper that was led by Antoine Coley, who's an organizer of this workshop, as well as the great Jean-Baptiste Moret, whose work I encourage you to read all of, as well as Dinesh Terapur. And in, basically in 1 to 2 minutes, we were able to get robots to adapt really rapidly to damage. And the idea here combined MapElite with some other flavor of machine learning, which was Bayesian optimization, which shows the benefits of taking the QD ideas or any other ideas from our community and hybridizing them with other flavors of machine learning as one recipe for success. Another paper that we did that, which was also in Nature, this time in 2021, just a few months ago, also took ideas from MapElite and quality diversity and combined them with other flavors of machine learning to great effect. In this paper, First Return, Then Explore, which covers the Go Explore algorithm, which I want to tell you about now a little bit. So there's a grand challenge in reinforcement learning, which is effective exploration. Basically traditional deep reinforcement learning algorithms are terrible on hard exploration problems. That's either if their problem is very, very sparse, like Montezuma's Revenge, which kind of became a grand challenge for the field because our algorithms perform so terribly on it, or if the problem is deceptive, which is that it actually tells you the wrong thing to do. So in Pitfall, you get all these little tiny penalties if you do things wrong. So algorithms learn to just stand still, and therefore they never got any points, which is the wrong way to solve this game. So classic deep reinforcement learning algorithms, when applied to these kind of problems, are terrible. They get like 0 or a few points on Montezuma's Revenge, like 2,500 points. On Pitfall, they get 0 or negative. So people said, let's take intrinsic motivation off the shelf, which is a classic method. Basically, go do new stuff, kind of like novelty search. And they applied it here, and the result was it didn't work very well. So if you look at Montezuma's Revenge, here is this all these papers that barely made any progress on Montezuma's Revenge. Right before we published our first Go Explore blog post, there was one work by OpenAI. They got 11,500 on Montezuma's Revenge, which was a really big deal, and people were really excited about that. But it's still, so it helps to do intrinsic motivation, but it didn't help enough. And the question is, why doesn't it work better? So we thought a lot about that at Uber AI Labs. We were working on this, and we ended up diagnosing 2 pathologies in intrinsic motivation. One of them is detachment. So imagine if you color this maze here green, and green is new stuff, and you say, go get all the green. So first, the algorithm happens to go to the west side of this map, the left side, and it goes and it follows this purple trajectory, and it basically consumes all this green, if you will. It gets all this new stuff. Then by chance, down here in the bottom left-hand corner, it switches to the right map, because there's a lot of green over there too, and it consumes that in all the green on the right map. Then look at the world that it's left in. Its policy now does not remember how to get back to that green frontier. It is detached from that green frontier. Every random perturbation to the actions or to the weights of the network does not land it in the green. It just leaves it on the white. And so now there's no gradient here. It's completely detached from the promising frontier of stepping stones. So our proposal was to explicitly remember those stepping stones, where they are, and how to get back to them. Basically, they have a growing archive of stepping stones that previously were good, and then periodically sample any of them, go back to it, and see if you can go further from there. Another pathology we identified is derailment. So imagine if you're a robot and you can do really well. Imagine you can get all the way to here. Well, you don't know whether or not the reward in this environment is up on top of this platform, but you'd like to find that out. So what you really should do is you should go back to that place and go a little bit farther. But we don't do that in RL, evolutionary RL, or traditional RL. What we do is we perturb the policy somehow and hope that it gets to that platform. But most perturbations, because they're sprinkled throughout the trajectory of the policy, will knock it off the wall. Or if we apply it directly to the weights of the policy, we'll also basically eliminate its ability to climb this wall, because climbing that wall is really hard. So the insight here is that we should first return without changing anything, and then we should explore. And that is really, really important. That's the way to just jump up here and see if there's reward on top of that policy. So the overall algorithm looks a little bit like this. Basically, we're going to have a space like Montezuma's Revenge. We're going to start exploring the space. And every time we get to a new state within that space, we'll add that to the archive. If it's interestingly like a new space, basically, you have to have some measure of whether or not it counts as new. And then from that archive, we sample and we return to that location with no exploration added. And then we explore from there. Now, there's a lot of details to how we did that. You can look in the paper. But basically, this is an enhanced version of MapElites, or at least the ideas behind MapElites and quality diversity, which are basically have an expanding set of stepping stones and have the best way to get to each one of them, and then use them as stepping stones to try to go further and find additional stepping stones. So this avoids detachment because it remembers all those promising stepping stones it's been to. And I really think it's interesting to contrast intrinsic motivation in the classic way with this type of exploration. So intrinsic motivation is like exploring a house with a very, very bright but narrowly focused flashlight. You first shine it over here and you say, there's something interesting over there. Oh, there's something interesting over here. Oh, there's something interesting over there. And you slowly go around and explore the house. However, quality diversity and Go Explore is more like turning the lights on in the central room in the house, and then the adjacent rooms, and then their adjacent rooms, and systematically going out in an expanding sphere of knowledge of what you know about the world, which is going to prevent detachment and cycling and allow you to fully illuminate the entire house. So there's lots more details in the paper, but I want to show you that it worked really well. So Montezuma's Revenge, you can see here, most papers were basically getting effectively 0 on this scale. Go Explore got 660,000 points on average. And that was the best neural net gets like, basically an arbitrarily high score. We could get a score of 18 million or higher. We beat the human world record and achieve the strictest definition of superhuman performance. On Pitfall, with no algorithm had ever gotten greater than 0, we end up getting a score of about 107,000, which is very close to the max possible within that game. In robotics, we applied it also and showed that you can solve really hard exploration robotics problems where you only get a reward at the very end for, like, making a cup of coffee or putting these blocks in these cupboards, etc. And you basically Go Explorer really can solve these hard exploration problems, and then later you distill the results into a policy. So the implications for Go Explore are that I think it shows the value of porting ideas from our community and QD ideas to DeepRL, and reimagining them in a slightly different context, such as states instead of policies. So I think that the question is then, like, what's missing? Where should we go next? And I think the answer is, as I alluded to earlier, QD is great. It gives you a diverse set of high-performing agents, but it's still stuck within one problem. It's either solving Montezuma revenge or Pitfall or that robotics test, etc. What we really want are open-ended algorithms. If we really want Pillar 3 to automatically generate all of the learning algorithms, all the learning environments that we might need for an AIGA to go to AGI, then we need algorithms that will endlessly innovate. Just like we see in natural evolution and human culture, where you just keep inventing problems and their solution. And the question is, can we invent an algorithm like this? An algorithm that could, say, produce all of the marvels we see in the natural world, such as jaguars, hawks, and the human brain. So traditionally in ML, we pick each problem in turn and we attack it, and then we pick the next one. We don't want that, though. Natural evolution arguably invented the challenge of leaves high up in trees and their solution in caterpillars and giraffes. And then those become challenges for other things, like the predators of those animals. So a framing that I really like, which I think comes from Jean-Baptiste Mouret originally, is, can we create an algorithm that would be interesting to come back and check on in 1 billion years? That would be fascinating. And that is a grand challenge for all of you. So one salvo that we had recently in this direction is POET, or the Paired Open-Ended Trailblazer. The idea here is we're going to endlessly generate increasingly complex and diverse learning environments and their solutions. So the idea here is we're basically going to apply the QD ideas, but to environments now. We're going to have an expanding set of challenging environments that a policy has to solve. And we're going to generate a new environment and add it to that set if and only if it's not too easy and not too hard, and it's interestingly new or novel. Then in this case, we have a policy paired with each environment, and we'll optimize that policy to keep getting better and better and better on that policy, and we'll allow goal switching. So you'll see how that works in a second. So the environment domain here was these little obstacle courses with a very low dimensional environment of search space, about 5, I think there are 5 dimensions of variation, such as the height of stumps, the width of gaps, etc. The idea is to run through this without falling fast. So here's how it works. You start with a parameter vector that describes an environment, phi1, and then an agent, theta1, that is optimizing to solve that environment. You start doing optimization. At some point, once the agent gets pretty good, then you copy the environment to make a new environment, and you transfer in that policy so you get the benefit of transfer learning, and then you do it again and create a new environment. Maybe that environment was too hard for either theta1 or theta2, so you create a new environment. And once you have this new environment, you now have a choice. Should you transfer in theta1 or theta2? Well, because goal switching is at play, we don't know which one's the best one, so we try both. Whichever one happens to be the best, we transfer that in. This doesn't have to operate in a linear chain. Any environment can be cloned. Any agent can swap into that new environment. Maybe eventually you get this really hard environment, theta6. Initially, you thought that a copy of theta5 was the best way to solve that problem. But maybe you have an innovation over here in this environment that ends up, producing a better solution in, a phi3 environment. And that ultimately replaces theta6 because of goal switching and because you don't know where the innovations are going to come from when you're pushing in science, in technology, in art, and in machine learning. So here are some of the solutions produced by this agent. Every environment that you see here was automatically generated by the system. And every robotic behavior, was also automatically generated by the system. And all of this goes on its own once you hit play at the beginning of a run. So it's beginning to feel like the AI generating algorithm that could just kind of go forever and keep inventing new things, as long as you had a big enough search space in the environment. So here the agent gets better and better. Eventually, it's kind of pushing the limits of its little physical body. It's jumping pretty big gaps, pretty big stumps, rugged terrain, etc. So one of the things that I love about this work is we went in and we documented the goal switching was essential here. If you take any of the environments that the system generated and then and solved, and then you try to directly optimize to solve that environment, what we found is that you always fail, as long as the environment is like, one of the harder environments that the system generates. So here's a bunch of environments here. And what you see on the bottom is what happens if you directly optimize to solve it with the exact same algorithm that Poet used. The only difference is that Poet had this curriculum and this goal switching amongst this set of environments, and it performed, way better, which is what the X's are, the blue X's are at the top. So we even went back and said, okay, let's be even more fair. Let's not just try to directly optimize hard environments. We'll create a curriculum, a linear curriculum that goes straight from the original environment all the way to those hard environments. And we'll linearly interpolate the environments between the two to make the environment look more and more and more resemble the hard challenge. And that also, it worked better, but it still failed. There was always a point along that chain where something didn't work. And so you really needed goal switching to get to these things. You can't take a straight line path to every innovation, much like you can't take a straight line path to invent a microwave or a computer. So I want to show this example here. The agent starts out on flat ground and it's got this knee dragging behavior and a score of 298. Eventually, the system automatically generates an environment with stumps. Now, the knee dragging behavior is no longer good in the environment with stumps, so the agent gets tripped up. So eventually it learns to stand up. Now, it turns out that actually the system automatically transferred that agent back to the flat ground environment because we're constantly checking for goal switching. And boom, that is a faster, better walking gait that was not invented in the original environment. And with further optimization, it gets all the way to a score of 349. Now, we did the counterfactual. We went back to that flat environment and we just left that original agent and gave it a ton of compute, and it is stuck. It is on a local optima. It never stands up, and so it gets a much lower score. We then, after the original Poet paper, went on to an enhanced Poet paper. I want to tell you a little bit about those innovations. One thing we did was we made a more wide open search space. We used a CPPN instead of the hand designed search space. And you can see that all of the different types of environments that were generated there. We also then invented a domain general metric of whether or not an environment counts as novel, because we no longer knew how to measure novelty in the CPPN space. And we came up with this idea of the performance of all transferred agents, or PATA EC, performance of all transferred agents environment characterization, or PATA EC. So the insight here is that, if you have an environment like this flat ground environment, and it's produced this rank ordering of agents, if you produce a new environment and it produces a never before seen rank ordering of agents, there must be something interestingly different about that environment. There's something that matters to the agents that change their ordering, and therefore that's interesting. And that, if you think about it, that can apply in general, and it can always tell you if you have some new interesting challenge. What's nice is that if you invent an environment that has a different pattern of clouds in the sky, for example, that does not matter at all to the agents, then you won't see a different rank ordering. So this only focuses on differences that matter, which is kind of cool. It also, if you invent a new kind of thing that matters, but only matters if all the agents are Einsteins, it's like impossible for it to matter for any of the current agents. It also doesn't have any effect, which is cool. So another thing we invented in Enhanced Poet is a way to measure progress in this type of open-ended system. We call this the cumulative number of novel environments created and solved, or ANNX. The idea is that you'll just count the number of environments that the system generated that are not initially too easy or too hard, but also that are eventually solved. This is kind of like a measure of learning progress in these systems. And so, you get no reward for generating impossible challenges or too easy challenges. You have to generate something that is, just right, but also learnable. And when we put all these things together into Poet, what you get is this much, much more healthy learning dynamic that doesn't flatline, but just keeps going. And so, who knows, at least within this search space, these things can kind of innovate forever. At least we haven't seen the end of it. And of course, what we really want to do is apply it to a more, even broader search space and more compute and see what happens. So all of these different environments were generated and solved by this system. And it's fun to see this little agent run around and solve these wildly different environments. But one of the things that I am most proud of is not just that the agent can, solve a variety of different environments, but like how healthy the learning is. So if you look inside, what you see is this phylogenetic tree that radiates out. It creates a whole different species of environments and keeps riffing on that theme. But simultaneously, it's inventing a different species, and then maybe that species produces a new adaptive radiation of types of environments, and all that's happening within the system. It also invents this funny challenge here, where you wouldn't think the agent can do that, but sticks the landing. So recently, this POET work was applied to real robots. They basically coded up POET, ran it inside of a simulator, and then dropped it in a bunch of real robots. And here it is out there in the world doing things in really, really, really hard terrain. So I find this very kind of inspiring that a learning-based system can do this. So I also think it's interesting to think about POET in, a really, really rich environment where you have, lots of big obstacles, markets, other agents you need to communicate, you need to trade, you can basically have aerial predators, et cetera. What would POET do if we put it in this sort of a world? I think it's inspiring. So the future work of POET is to apply it to other domains, maybe have it generate the reward function, bigger search spaces, combine it with other pillars of AIGAs. For example, meta learning needs a huge distribution of environments. You could use this to generate the environments. There are other combinations you can think of. I think that, I can just tell you from personal experience, the machine learning community is very excited about quality diversity right now. They're very excited about open-endedness. So our work is paying off. It is inspiring people. And I think that the sky is the limit. We should keep going and investing in this direction. So to my overall conclusions for the talk, AI generating algorithms, I think, are likely to be the fastest path to AGI. All of the work that I've just talked about increases my confidence in that. I also think there's lots of work I didn't mention, and that work is increasing. So increasingly the community is focusing on this. I think we're at a tipping point, and we're seeing that this kind of learn everything based meta learning solution and automatically generate the environments in the curriculum is paying off. So as Wayne Gretzky's dad says, if you're trying to decide, where to go, skate to where the puck is going, not where it is. So if you're picking where you want to invest your research career, I would focus on this sort of a AIGA path to AI, because that is, in my opinion, where the puck is going. I think that, the final slide here is that I think there are opportunities for this community in all three of the pillars, especially pillar 3, because that plays to our strengths. And I also think there are opportunities to combine all three. You don't see a lot of people working on that. So that's a rich terrain for people to pick low-hanging fruit in. So the work described here, I think, shows the potential of this paradigm, but really, I think the exciting work lies ahead, the kind of work that all of you and the rest of the people in the community will do. So I hope that you'll join in this effort. It's really fun, it's really exciting, and I'm very excited to see where it goes. Thank you very much.